All right, so today we are going to start talking about synthesis and decomposition reactions. And we're going to talk about them together because they are exact mirror images of each other. So it should make a little bit of sense as we go that if you learn one, you're pretty much learning the other because they're exact opposites. That's why I put them in the notes sort of right next to each other so you could see how they're related. Okay, so let's start with synthesis. Synthesis reactions are usually exothermic, and that's because the products, the thing that we're forming, are a bit more stable and lower in energy than the reactants were. So one example of this would be just two free elements coming together to make a binary compound. And so the word synthesis means to make, right? If you synthesize something, you're making it. So with this first example, you can see it really straightforward why this would be. So for example, let's say we have some calcium reacting with nitrogen, okay? So nitrogen, by the way, is Brinkelhoff. So even though it's a free element, we have to put that 2 there. And so we're going to recognize this as a synthesis reaction because there's really only one thing that can happen when I put together 2 free elements from the periodic table, and that is for them to come together. And when they come together, they're going to form a binary compound. So it's going to be, in this case, the ionic compound, calcium nitride. And so all we have to do is remember how to balance charges when we put them together. And since calcium is 2 plus and nitride is 3 minus, we are going to need 3 calciums and 2 nitrides in order to balance. So, and then in terms of balancing the equation, which of course we only do after we've written the balanced, the formula correctly with charges balanced, we would have to balance by putting a 3 in front of calcium. And there we go. And that is our first type of synthesis reaction. Free element plus free element come together to give us a binary or 2-part compound, the 2 parts being calcium and nitride. Okay, so see if you can do this one. Maybe pause the video and try it on your own. Let's go with aluminum reacting with chlorine. Okay, so what you should have gotten there was just aluminum chloride. And again, the only thing that you have to do is think about charges and balancing. So aluminum is +3, chloride is -1. So I should have 3 chlorides, which does give me an imbalance of chlorines. So if we go ahead and balance that, we could do that by getting to 6 on each side. So 2 aluminum chlorides and 3 chlorines. All right, and so that's it. That's type A, free element plus free element gives a binary compound. And of course, decomposition would be just the opposite. And in fact, I could even take my product of my first reaction and basically just flip it completely around. So if I make the product, calcium nitride, into my reactant, in other words, we're starting with a binary compound, right, calcium nitride, and we're breaking it up into free element plus free element. So decomposition, to decompose, means to break something down, right? And that's exactly what we're doing here. Now notice, even though it's a free element, I have to write my Brinkelhoff elements with 2 subscripts. So N2 rather than just N. But the Ca can be by itself. And then of course to balance the calciums, because I have 3 on the left, I have to put a 3 out in front on the right. And these are just the opposite. So they're usually endothermic. So calcium nitride is actually much more stable than elemental calcium or nitrogen. And so the only way to get it to change, in other words, to break the old bonds between the calcium and the nitride, is to add a bunch of energy. So this is endothermic. So just like synthesis is exothermic, decomposition in the exact opposite direction is going to be endothermic, or absorb energy. Okay, we're going to go through 3 more types. These are a little bit more prescriptive. And so what I mean by that is they're very specific. So if you see a metal oxide and water, Okay, and so metal oxide, for example, would be like, could be magnesium oxide. So that would be a metal oxide, so the metal being magnesium. If that reacts with water, hopefully you'll recognize this as a synthesis reaction and not a double replacement. Because if it were double replacement, you'd have two ionic aqueous solutions. And so while magnesium oxide could be an aqueous solution, the water, of course, is not, right? It's just a molecule, it's just water. So once you see that, and you see that it's not two aqueous ionic compounds, you know not to treat it like a double replacement. You're going to treat it like a synthesis. And it's a very specific type. It's going to give you a metal hydroxide. And of course, the metal is just whatever metal was originally paired with oxygen is now going to be paired with hydroxide. So your product would be magnesium hydroxide. And then, of course, thinking about the charge of magnesium being +2, hydroxide being -1, we would need 2 hydroxides. And then this one, I believe, is already balanced because we do have 2 oxygens and then 2 oxygens on the left, 2 hydrogens, and of course 2 hydrogens on the left as well. So metal oxide plus water gives us a metal hydroxide. All right, and if we flip that around and we do the decomposition version, so the exact opposite, maybe we'll just randomly pick a different metal. Let's say we have copper 1 hydroxide. So in other words, CuOH. Okay, so you're going to recognize that as a metal hydroxide, hopefully. And so you know that that's going to be just the opposite of what we just did. So now the metal oxide and water is on the right side of the equation. And of course our metal oxide is copper 1 oxide. So notice I am assuming the charge does not change. So if it was copper 1 on the left, because it was a 1-to-1 ratio with hydroxide, it's still going to be copper 1 on the right. And so since oxide is -2, I would need 2 copper 1 ions. And then of course my other product is simply water. Now this one I believe does need some balancing, right? Because our copper has 2 on the right and only 1 on the left. And that also balances my oxygen with 2. And then over here I have 1, 2. And hydrogen with 2 and 2. So there we go. All right, on to the next type. This is very similar. We still have a metal oxide, this time reacting with we're reacting with carbon dioxide instead of water, and we're getting a metal carbonate. So let's go with our metal oxide. Let's say this time we have aluminum oxide, Al2O3 plus CO2. So again, that second substance, that CO2, that's not ionic. So even though I am combining 2 compounds, if they're both ionic, then it's double replacement. But if one of them is covalent, like water or carbon dioxide, then we have a synthesis reaction. And in this case, it's going to synthesize the metal carbonate, aluminum carbonate. And aluminum is +3 and carbonate is -2. So hopefully you could figure out here that our formula would be Al2CO3 parentheses 3. All right. Balancing wise, it looks like I have 3 carbons on the right. I can't really balance carbonate because it doesn't show up as a polyatomic ion on both sides. So I have 3 carbons on the right, so I probably would want to put a 3 in front of CO2. And that gives me 6 oxygens, but I also have 3 here, so that's 9. And then luckily I have 3 times 3. Sorry, that is a 3 there. I have 3 times 3 on the right, so that's 9 as well. Okay? And so now for the other side, for the decomposition side, we're just going to do the exact opposite. We'll pick a different metal. Let's say this time, let's go with iron 2. Okay? So Fe 2+ paired with carbonate would just be a 1-to-1 ratio. And you're going to say, okay, that's a metal carbonate. That's going to make a metal oxide. So iron 2 oxide, which would just be FeO, and then carbon dioxide. So I don't really have to worry about charges or balancing charges, it's just carbon dioxide, right? And it looks like, if I'm not mistaken, this one is already balanced. Okay, last but not least, we have a metal chloride plus oxygen. So a metal chloride, I'll just pick one at random. Let's go with potassium chloride and oxygen. So you might be thinking, okay, something plus oxygen, that's usually combustion. And while this will be exothermic-like combustion, it's a little different because it's not a hydrocarbon that's reacting with oxygen, right? It's an ionic compound. It's a metal chloride that's reacting with oxygen. So KCl plus O2 would give us a metal chlorate. And by chlorate, we mean the polyatomic ion chlorate. So in this case, it's just going to give us KClO3 is chlorate, and K is plus 1, and chlorate is -1. So it's just a 1-to-1 ratio. This one's a little trickier because I have 2 oxygens on the left and 3 on the right. So I'd probably try to get to 6 on each side. So maybe a 2 in front of potassium chlorate will give me 6 oxygens on the right, and a 3 in front of O2 on the left would give me 6. And then in terms of both potassium and chlorine, I would need to put a 2 on the left. And there we go. Should be all balanced. All right, and then finally, just the exact opposite of that. We'll pick a different metal, though, this time for our metal chlorate. Let's go with calcium chlorate. So CaClO3 2 because of the calcium being +2 charge. So a metal chloride. So calcium chloride, and then just oxygen, O2. Of course, oxygen is Brinkelhoff, so we have to make it diatomic. All right, let's see. This time it looks like we need to balance, well, we already have 6 oxygens on the left. So if I put a 3 in front of O2 on the right, that should give me 6 there as well. And then I have 2 chlorines, distribute the subscript, I have 2 chlorines, and I have 1 calcium, and I have 1 calcium. So there it is. So hopefully this makes a bit of sense. You know, there is a bit of memorization with this. You just have to remember to classify these things. And if you just sort of associate the things on the left and the right together. So for example, if you remember that a synthesis reaction where carbon dioxide is one of your reactants, that's always going to give you carbonate. So CO2 gives you CO3. You know, a chloride and oxygen gives you chlorate. It kind of makes sense. The metal oxide and water gives you the metal hydroxide. They obviously go together because of course, by definition, they have to contain the same atoms. And then if you can do them in one direction, then by definition you should be able to do them in the other direction because it's really just flipping it around so that your products become your reactants. All right, so go ahead and we're going to talk about E and F later on, but do attempt assignment 4.4. Do your best for those 8 problems, and you can just match them back to your notes. So the first thing you always want to do is classify each thing, and if you don't have room to write that in there, at least do it mentally so that you can look at this and go, oh, if I have MgO plus CO2, well, MgO is an example of a metal oxide. CO2 is carbon dioxide. And the reason I ask you to do that is just to get in the habit of classifying what you have on the reactant side, because that's going to be what jogs your memory and helps you understand what to predict as products.